So let's see, this is section 6.5. And part of the reason that we're doing this now is because this is related to what we've done with right triangle trigonometry. It's related to what we've done with vectors, and vectors are related to what we did with right triangle trigonometry. And just so you know, you'll also hear this called polar form of a complex number. Trig form, polar form mean the same thing. And next semester we will study a little bit. We'll talk about polar coordinates, and then that will make a little more sense. Polar just has to do with angles. All right, so a reminder: a complex number is a number a plus bi, where a and b are real numbers, and I is the square root of -1. And this also means that I squared is -1. And I, we call I the imaginary unit. I is an imaginary number. It's kind of unfortunate that they named it, they used that term imaginary, because it kind of sounds like it means it doesn't exist. But the reason they used imaginary is to contrast with real numbers. So they could have named it anything. It could have been a Fred number. They just chose the word imaginary. So what we're going to do today is imagine, no pun intended, but we're going to think about complex numbers on what we call the complex plane. So let me draw a set of axes. And this is going to be our complex plane. And on the complex plane, instead of the x-axis, we think about this being the real axis. And the y-axis, we think about being the imaginary axis. So this complex number, a plus bi, what we're doing is we're thinking about it being, telling us, will we go a units in the real direction and b units in the imaginary direction. So we think of this like the x-axis. This tells us how far to go in the x direction, and the b tells us how far to go in the y direction. So we have this point a plus bi out here in the complex plane. And I'm going to call this complex number z. Z is instead of using x's for complex numbers, traditionally we use z's. So there's z equals a plus bi out there in the complex plane. What we're going to think about is connecting that point with a little segment from the origin. So we're drawing sort of like drawing a little vector to that point. And we're going to imagine, or going to think about this little right triangle that we get in the complex plane. And this side of the triangle is A, and this side of the triangle is B. We've done this when we talked about right triangle trigonometry. We've done this when we talked about vectors. The exact same idea. The length of this hypotenuse, the distance of the complex number from the origin, we call the absolute value of z. And z is just the length of that hypotenuse. We say is an absolute value of a plus bi, which is the square root of a squared plus b squared. It's just the length of that hypotenuse. So the absolute value of a complex number is, we can kind of think of it as the magnitude of that number. Where with vectors we use 2 bars, with complex numbers we just use the 1 bar. So that's the length of that hypotenuse. So for a quick example, if we wanted to find the absolute value, absolute value of z equals 4 minus 3i. So the absolute value of z is the same as saying the absolute value of 4 minus 3i is just the square root of 4 squared plus negative 3 squared, which is 5. And if we think about this graphically, what we have is we're going 4 units in the x direction, 3 units, negative 3 units in the y direction. There's 4 minus 3i. And we have this little triangle here. That side's 4. That side's negative 3. And that side is 5. Exactly like we thought about with right triangle trigonometry, and exactly like we thought about with vectors. And I'm going to add one piece of information. Oh, no, I'll add it on the next picture. All right, so absolute value for a complex number means its magnitude. Means how far away from the origin is it? It's the length of that little segment. It's a hypotenuse of this little triangle that we draw. All right, so we're good so far. Well, now what we're going to do, just like we did with trigonometry, just like we did with vectors, is we're going to think about this angle here. And we're going to write this complex number in terms of this angle that we make with the positive real axis. So we're going to talk about the trig form. So I'm going to draw the same picture, a little picture of the complex plane. And this is our imaginary axis, and this is our real axis. And we have our point, our complex number z equals a plus bi. And we're going to draw a little segment out. We're going to make a triangle. That's A, that's B. And we're going to talk about this angle theta that we make with the positive real axis. Well, the magnitude or the length of this hypotenuse is the absolute value of z. And for what we're going to do here, we're going to call that r, like a radius, like we did when we talked about trigonometry. We can think of this point rotating around all the way around the axis. We'd get a circle with radius r. So the magnitude of or the absolute value of our complex number, we're going to call r. Well, this side of the triangle from SOHCAHTOA, from our right triangle trig, A is r cosine theta. And B is r sine theta. We're just doing opposite over hypotenuse, adjacent over hypotenuse, solving for that side. So in trig form, we can say that z equals r cosine theta plus I sine theta. This part is from here is A, and this part, oops, I forgot my R. That part is B. Those little pieces of that triangle. And often you'll see this written as r times, we factor out the r, cosine theta plus I sine theta. We call this the trig form or polar form of a plus bi. We call R the modulus. And we call theta the argument. So modulus is just another name for the absolute value of a complex number. The magnitude, the length of that hypotenuse. Called the modulus, and we call the angle theta, we call it the argument. And one really interesting thing, an extension, we talked about it a little bit in my other class this morning, is that r cosine theta plus I sine theta equals r e to the I theta, where e is the e from exponential functions. So that's a really, where I said where you get close to the kind of math that you paint pictures with, this is kind of that, where we get kind of close to that. So there's a relationship between trigonometry, complex numbers, and exponential functions. They're really not different things. They're all kind of all tied together. It's really pretty amazing. And I picked out my shirt especially for today's class. All right. So questions so far? So what we've done is we've represented this complex number. We're thinking about it like a little vector in the complex plane. Once we have the x direction, the y direction, just like we did with vectors, just like we did with right triangle trigonometry. Oh, and I forgot one piece of information here. Just like we've done before, tangent theta is b over a. Opposite over adjacent. Sine theta over cosine theta. All right, so let's look at a couple of examples of converting back and forth from standard form, a plus bi form, to trig form, or from trig form to complex form. And then we might be thinking, well, why in the heck would we ever want to do this? And we'll start talking about that. All right, so let's write z equals -2 plus 2i in trig form. Now it might be helpful, just like we did when we were doing trigonometry, to draw a little picture. Well, there's -2 plus 2i. There's that complex number, and I'm going to draw the little segment there. The segment is just to help us visualize what the operations that we're doing. The point is the complex number. This point here. All right. Well, we need our angle. Tangent theta is 2 over -2, which is -1. And what quadrant are we in? Second quadrant. So we need a second quadrant angle whose tangent is -1. So this is a unit circle problem. What angle in the second quadrant has a tangent of -1? 3 pi over 4. And we need so this is our argument. We also need to find our modulus. R is the absolute value of z, which is the square root of -2 squared plus 2 squared. So it's 4 plus 4 square root of 8, which is 2 square root 2. We simplify. So negative 2 plus 2i equals, in trig form, 2 square root 2 cosine 3 pi over 4 plus I sine 3 pi over 4. Two different ways of writing the same number. Yeah.
Why did you decide to use tangent in the beginning?
Because we know the tangent of the angle is the opposite over the adjacent, or the y over the x. So we use a tangent to find the angle, our argument in general. So this is our modulus. So we found our argument, found our modulus, and we write our trig form. Any other questions on that example? Let's go the other way. We want to write for cosine 5 pi over 6 plus I sine 5 pi over 6 in trig form. Or sorry, in a plus bi form. Well, what this problem is asking us to do is find these values and distribute that 4. Well, this is going to equal 4 times, what's the cosine of 5 pi over 6? Negative square root of 3 over 2 plus I times the sine of 5 pi over 6. 1/2. And now I'm going to distribute. So I get negative 2 square root 3 plus I plus 2I. And what this is telling us, if we draw a little picture here, this is telling us our angle is 5 pi over 6, so we're over here. And the length of this segment is 4. And that angle is 5 pi over 6. So and this point would be negative 2 square root 3 plus 2I. So graphically, that's what that's telling us. All right, so this is all nice, similar to vectors, similar to right triangle trigonometry. Why do this? Well, one, because it's fun. But two, let's think back when you've talked about complex numbers before. How would you multiply something like 2? How would you do 2 plus 3i times 5 minus 7i? What do you have to do to do that multiplication? Do we remember? In general, what do you do when you multiply two parentheses like that together? Foil. We have to foil. We have to distribute. So I'm going to say foil. And remember that I squared equals negative 1. So we combine like terms. We FOIL this out, combine like terms. Remember that I squared is negative 1, and then rewrite it. And do we remember how we would do 2 plus 3i divided by 5 minus 7i? What do we have to do that operation? We by the bottom, but what do we do at the bottom? There's a special word that we used. The conjugate. So we have to multiply the numerator denominator by the conjugate of the denominator. 5 plus 7i, 5 plus 7i, and we multiply that out in the numerator and the denominator. So then we have to FOIL, etc. It's quite a process. Now imagine if we had something, thinking along these lines, what if we had something like 2 plus 3i to the 12th power? Imagine doing that process. You'd have to multiply 2 plus 3i times 2 plus 3i times 2 plus 3i 12 times. That's a huge amount of work. One of the reasons that we represent complex numbers in trig form is we can simplify this entire process. Well, then I'm going to mention one other thing. What if we wanted the fourth root of 2 plus 3i? So this is, I'm going to say this is messy. Fourth root of 2 plus 3i, we have no idea how to do that. We don't have a process for this. But with the trig form of complex numbers, we will be able to do this. Find the fourth root of a complex number. And why would you want to find the fourth root of a complex number? Well, one, because it's interesting and an interesting idea to find the roots of complex numbers. But two, complex numbers, believe it or not, they do come up in application. Complex numbers come up in electrical circuit design. Complex numbers come up in solving various kinds of what we call differential equations. Anything that has to do with subatomic processes, when you talk about quantum mechanics, the equations that describe quantum mechanics involve complex numbers. Often in fluid flow, the equations that describe fluid flow involve complex numbers. So they do come up in application. That's kind of the painting the fence stuff about complex numbers. But just the idea that you can find a fourth root, that's a pretty cool idea. All right, so let's talk about how trig form of complex numbers helps us out here. We're going to talk about multiplication and division. So we want to see how the trig form of complex numbers is going to help us with this process of multiplying and dividing complex numbers. And then we're going to extend, we will do that on Monday, we'll extend the multiplication to the idea of finding powers of complex numbers. And the reverse process of finding powers is finding roots. So we'll be able to find powers and roots of complex numbers. All right, so let's say we have one complex number that is R1 cosine theta 1 plus I sine theta 1. R1 is some number, we have some angle here. And Z2 is some other complex number in trig form. R2 cosine theta 2 plus I sine theta 2. And we're going to multiply these two complex numbers in trig form. So make sure you start kind of on the far left side of your paper, because there's some writing that we have to do here. So we're going to multiply these together. So the numbers R1 and R2 are just real numbers. They're just the magnitudes of these things. So they just end up getting multiplied together. R1, R2 times cosine theta 1 plus I sine theta 1 times cosine theta 2 plus I sine theta 2. Well, now we're going to multiply these two things together. And we think, in the backs of our heads, we think, well, a lot of times when we multiply things, cosines and sines together, things happen that involve identities, that make things look better. That's what we should think about identities. Some of us think that when we think of identities, we think things look worse. But really, they look better. R1 times R2, we're going to FOIL this. So I get cosine theta 1, cosine theta 2. That's our first. Our outside is plus I cosine theta 1 sine theta 2. My inside, I get plus I times sine theta 1 cosine theta 2. And for my last, I get I squared, which is negative 1. So I get minus, because I get an I squared there, sine theta 1 sine theta 2. Now I'm going to put all the parts that don't have i's together and all the parts that do have i's together. So put the real parts together and the imaginary parts together. R1, R2, cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, plus I times, and I'm going to stop there for a second. Does this look familiar? Cosine u, cosine b, minus sine u, sine b. There's an identity there. And for the second one, I get sine theta 1, cosine theta 2. And I'm going to write this in the other order, so I get cosine, and then cosine theta 1, sine theta 2. Does this look familiar? We have sine u, cosine b, plus cosine u, sine b. Those are our sum and difference formulas. This is R1, R2 times the cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So what this tells us is to multiply we multiply the moduli moduli is plural for modulus. So we just multiply those two numbers together. The moduli are real numbers. And we add the arguments. We just add those two angles together. So multiplying complex numbers has to do with adding rotations, because we can think of one complex number being rotated a certain amount, another complex number being rotated another amount. Well, to multiply those two, we're adding those rotations. So multiplication of complex numbers has to do something to do with rotations and adding those two. Where with real numbers, we think of multiplication having to do with making lengths bigger. We make the length bigger, but we're also adding rotations. So that gives us kind of a visual representation of multiplication in the complex plane. It has to do with adding rotations. I'm not going to go through the process, but I'm going to say similarly, we go through a similar process. Z1 divided by Z2 is R1 divided by R2 times the cosine of, what are you going to guess we do to the angles when we divide? Subtract theta 1 minus theta 2 plus I sine theta 1 minus theta 2. To divide, we divide the moduli and subtract the arguments. So division in the complex plane has to do with subtracting rotations. And we would show this kind of in the same way that we did for the first one, but we have to multiply the numerator and denominator by the conjugate and simplify. It's a lot more work, but it involves a similar kind of process. So this is one of the reasons why it might be beneficial to write complex numbers in trig form, because multiplication and division is way easier. And the multiplication piece is going to let us figure out powers and roots of complex numbers. Because a power is just repeated multiplication, right? Something to the third power is something times itself times itself. Well, we just continue this process, and we'll have a process to find the 127th root, or 127th power of a complex number very, 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 very easily. compared to the way that we would have to do it before. And it would also let us calculate the 127th root of a complex number very, very, very easily. Actually, we'd get 127 127th roots, but we'd be able to calculate them pretty easily. All right, so let's look at one example having to do with multiplication and division. Any questions so far? All right. Let's say Z1 is 8 cosine 120 degrees plus I sine 120 degrees. And Z2 is 6 cosine 150 degrees plus I sine 150 degrees. And we want to find Z1 times Z2 and Z1 divided by Z2. Well, Z1 times Z2 is, multiply these two together. 6 times 8 is 48. And we're going to do the cosine of, excuse me, 100, 120 plus 150, which is 270 plus I sine 270. And now we're going to say, well, what is the cosine of 270? What is it? 70? 0. And the sine of 270? Negative 1. So this is negative 48i. So these two numbers multiplied gives us negative 48i. Z1 divided by Z2 is 8 divided by 6 times the cosine of 120 minus 150. Negative 30 plus I sine negative 30. Oops, yeah, that's good. I need one more here though. And I can reduce this and say that's 4/3. Cosine of negative 30. Square root of 3 over 2. And the sine of negative 30? Minus 1/2 I. And so when I distribute, I get 2 square root 3 over 3 minus 2/3 I would be those two numbers divided. And this is going to give us, we'll talk about on Monday, the ability to find powers and roots of complex numbers. Questions? Okay. Before I put the homework up, let me show you. So this kind of related to what we're talking about today. You've probably seen this, seen a picture of this before. It's called the Mandelbrot Set. So let me get that pic. That's a decent one. There's a good picture, relatively good picture of the Mandelbrot Set. So Mandelbrot Set is a fractal. So what this is the complex plane. 0, 0 is, I think 0, 0 is here somewhere, but this is definitely the real axis. And what happened with the Mandelbrot set is this is a function where the variable is complex number. And so what you do with this function is you do, I think Mandelbrot set is z squared plus a constant. So you take your number, you square it, and you add a constant, and then you do that again. You square it again, add a constant, square it again, add a constant. So the black part is, if you do that an infinite number of times, the points that are in the black area of the complex plane, that process of squaring and adding, squaring and adding, stays finite. And outside of that area, eventually those, when you multiply those numbers, they get bigger and bigger and bigger, and they go to infinity. And the colors, what they do is they code with colors how fast that happens. And the boundary of that set is really complicated, but you can see little copies of the set itself. So you get all these little tiny little copies, and it continues on infinitely. You can kind of follow these threads, and you get tiny little copies of the Mandelbrot set. So that's one example of kind of the picture painting math that I was talking about that comes out of complex numbers. Mandelbrot set, when I was in high school, my English teacher told me about fractals and the Mandelbrot set, and that's what got me interested in math, was my English teacher in high school. So, just a little sideline there. Homework. Back to hammers and nails. EOE, every other even. There we go.